Hello and welcome to another walkthrough. Now this time it will be Edexcel A-Level Further Mathematics Paper 3C Further Mechanics 1 June 2025, which I have never seen before. So this is going to be a blind solve for the entire paper under the real exam conditions. So along the walkthrough, I might be making mistakes, which I'll correct if I realize in the walkthrough, but if I don't, I'll annotate the video and I'll try to explain the worked solution and the thought process as simply as possible. At the end of the walkthrough, I'll mark the paper anyway. For those of you who make mistakes a lot of times, you might benefit from seeing me making a mistake and correct it later. So this walkthrough is not meant to just show you the destination of the solutions, but also show you the journey to the destination. If you feel like jumping to a particular question, you can use chapters in the description. Otherwise, stick around. You might be getting some tips along the way. If you are ready, I'll see you in there. Okay, here's the paper, and I'm going to start the timer now. Okay, let's go, guys. Number 1. A particle A has a mass 4m and particle B has a mass 3m. Particles are moving along the same straight line on a smooth horizontal table. The particles are moving in opposite direction towards each other and they collide directly. So this is not oblique collision. As a result of collision, the direction of motion of particle is reversed. Each particle is reversed. So it's going to look like going in like this and going out like this, right? So this is 4m and 3m for A and B. And then we don't know about the initial speed, or we do. Immediately before collision, the speed of A is u. Okay, A is 4m, yeah? And the speed of B is ku, okay? Where K is a constant. Yeah. And immediately after the collision, the speed of A is 2v and the speed of B is 3v. The magnitude of impulse received by A in the collision is 20 mv. Find u in terms of v only. Okay. So impulse received by A, we need to calculate the change in momentum of A, right? So ma VA minus UA, yeah? And MA is just 4M. The impulse we got to be 20 MV, yeah? Okay, so VA, so VA, the speed of A after the collision is 2V. So 2V, well, because it's going in opposite direction, so this will be plus instead, yeah? Because they go in opposite direction. I mean, if they went in the same direction, it would have been minus then, but they went in opposite direction. They go in opposite direction here, u and 2v, yeah? So UA here would be just u. And then we find u in terms of v. So m cancel here, so 20v equals 8v minus 4u. We want u in terms of v, so u as a subject would be minus 12v divided by 4, so minus 3v. Because this is a magnitude, so actually, let me make that positive actually. Can we do that? V subtract, yeah. So this will just be u equals 3v. Okay? Yeah, it should be. Hang on. Minus 3v. Wait. 2v is for the speed of A. Yeah. Oh, sorry. I said plus, right? Why did I do minus there? Should be plus here. Yeah. Okay, so for cancel both sides, I get 5. V equals 2v plus u. Like that, sorry. Yeah. I always need a warm up somehow, right? In every paper, as you can notice sometimes. And then 3v equals u. There you go. So u equals 3v. Yeah. I think that's it, right? 5v and then 2 subtract, I get 3. Yeah, just need to be thorough a little bit there. Find the exact value of k. Okay, so k is the coefficient of speed of b there, right? So we just do conservation of linear momentum. So that would be 4mu minus, if we convert to the right as positive, yeah? So 4mu minus 3mku, yeah, equals, well, now it's to the right would be that one would be negative now, which is 8mv minus here, yeah, negative, and to the right 3m times 3v would be plus 9mv, yeah, because we already know that u in terms of v would be 3v, so we're just going to plug that in. Okay, 3v here equals minus 8m, so that's, these can already simplify to mv, yeah. Now we're just going to cancel everything like the m, the v, the m, the v, and the mv here. So this is 12 minus 9k equals 1, not 0. Got to be careful there. So that means k would be 11 over 9. That would be exact, right? Let me just double check everything. So 4mu to the right, yep. Speed, initial speed is u, yep. Minus 3mku, yep. Okay. And then after the impact is 2v to the left and 3v to the right. And then I put linear conservation of linear momentum here. Okay, minus 8mv to the left after the collision, 9mv to the right after the collision, add up to mv, plugging u as 3v. So that would be m and v cancelled, so 12 minus 9k equals 1. Yeah, I think I'm happy with everything here. So that's it. Okay, that's question 1 done. Question 2, sorry, 2 is here. Okay. Question 2. A van of mass 900 kilograms is moving along a straight horizontal road. When the speed of the van is v, the resistance to the motion of the van is modeled as force of magnitude 50 v, not 50 newton. The engine of the van is working at a constant rate of 12 kilowatts. At the instant when the speed of the van is v, the acceleration of the van is that. Using the model, find the value of v. Okay, straight horizontal road, so let's make that a car, a van, sorry, and then it's moving as an acceleration of 0.2 meters per second squared. So there is a driving force from the engine, which will be F equals 12 kilowatts divided by the speed at which it's moving, which is given to be V, which is actually what we want to find. Okay, and there is a resistance to the motion modeled as a force of magnitude 50 V. That's a little v, right? It's a different one. When the speed of the van is v. Oh, okay. So this is the same v. Yeah. Okay. Yeah, there you go. And then we have, yeah, that's it. Okay. So sigma f equals ma. So we do 20,000 divided by the speed. Yeah. Minus the force of magnitude 50 v equals m, which is 900, times a, which is 0.2. That's everything, right? And then seems like we need to solve quadratically here, because you have 1 over v and a v term there. So if I multiply by v, I would get minus 50 v squared here, just tidying up a little bit. And then this one will multiply to 180. And then if you multiply that by also a v, you would have a minus 180v here to the same side of minus 50v squared. And of course, the 20,000 would be a plus, 12,000 would be a plus, 12,000 down with no v. Yeah, everything is fine here, I guess. And then we can solve quadratically. Yeah, so I'm just going to use a calculator to just check which one works. And we can just pretend like we solve quadratically, you know, as in using the formula. So minus 180 and then 12,000. There we go. Oh, that's not so nice. Okay, so basically one of them should work at least. Okay, yeah, I'm gonna take that value, but let me just plug in the value first. So v equals 180 plus or minus square root 180 squared minus 4 times a times c, like that, yeah, divided by 2 times a. So we're gonna get a positive and a negative one. So the positive one is 13.796 and the negative one is minus 17.396, but we reject the negative one because this is a speed. Okay, let me just check all the math again just in case, you never know, but I think I'm okay with the physics there. And then the math here, multiply V out, just double checking. Yep, so I'm fine with that. So V equals 13, just gonna make 3 significant figures, so 13.8 meters per second. Yeah, that's part A done. Later on, the van is moving up a straight road that is inclined at an angle alpha to the horizontal, where sine alpha is that. Okay, alpha here. When the speed of the van is V, the resistance to the motion of the van from non-gravitational force, speed is V now, okay, and the resistance to the motion of non-gravitational force, motor as force, again 50V. Okay, non-gravitational force. So we still have a gravitational, which is mg sine alpha. All right, another one there. And then, yeah, of course, when the van is working at constant u, okay, the engine of the van is working at constant, right, so that would be 15,000 over u. Yeah, like that. Using the model, find the value of u. So basically, that u and this would be the same, yeah? So we put it as this. Because they just try to use different letters, but actually if you want to find the speed u, you just have to plug that u into 50V anyway. So we do, again, this is constant speed now. That means resultant force equals 0. And we don't need to worry about the other direction perpendicular to the slope. Yeah? So 15,000 divided by the capital U minus 50 capital U minus mg, so m is that, right? G 9.8, and sine alpha would be 1 over 12 equals 0. Okay, that's it. Yeah, because they are balanced here. Let me check everything again, yeah, if I'm not missing anything. But yeah, this is u, right? Okay, no acceleration there. Yeah, okay, so that's straightforward 4 marks there. Oh, quadratic again. All right. Yeah. Okay, so let's simplify that. 900, you know, the third term there. So 900 times 9.8 divided by 12. Well, that's actually 735 there. Is there any common? No. Okay. So again, I'm just going to solve quadratically again. So minus 50u squared, just doing the same way there. And minus 735 big U and plus 15,000 equals 0. Just like that. Multiply u out, yeah. And then solve quadratically. Let's see. So we have minus 50 minus 735. Is that minus? Yeah. And then plus 1500, 15,000. Okay, gonna note down the value. 11.465, and the other one minus 26.165. At least the numbers look consistent to me, as in the decimals. So u equals minus b plus or minus square root b squared minus 4 times a times c, like that, divided by 2 times a, and equals that. So we reject that. Therefore, u is 11.5 meters per second. Now let's physically think about it, if it makes sense. When you go uphill, yeah, but well, power changes now. Power increases. So before we got the V to be 13.8, but that's not uphill. This is smaller and uphill, although the power is a little greater, but You also have the weight there. So okay, it's not out of ordinary here. It's just okay, I think. So we should be fine, I think. I'm going to take this value and go ahead and go do number 3 now. Okay, number 3. Particle P of mass 0.4 is moving velocity 7I when it receives an impulse of magnitude that. The velocity of P immediately after it receives impulse is that, where that. Okay, so basically this is just impulse equals change in momentum, and we do it in a vector way. So impulse of magnitude that, right? Okay, so change in momentum is m v minus u. So v is just 2 lambda I, right? If I multiply, so this is the final speed. Yeah, we do vector here. So 2 lambda I plus lambda j. Yeah, that's the velocity there after the impulse or the impact, minus the initial speed, which is 7I. Yeah, initial velocity. And then we have impulse here. Okay, so I'm just going to find impulse first in terms of m and everything. So I'm just going to change that to 0.4 already. In the brackets we have, so got to be careful with the I and the j here, yeah? So it's 0.4 times 2 pi minus 7I, yeah, plus pi j. And then this impulse has a magnitude of square root 1.6, right? So if we find the, the magnitude of that vector, we equate that to square root 1.6, which will be square root of, so if you split the component, this is the I component, multiply with 0.4, so I'm just going to do 0. You can take the 0.4 out, right? Yeah. So I'm going to take the 0.4 out here, because you can do that. And this will be 2 lambda minus 7 squared plus lambda squared, just like that. Okay? Yeah. So if we square both sides, we get 1.6 here equals, that would be 0.16, right? If you square the 0.4, and this will be undone, the square root will be undone, so we get inside the square root, which is in the brackets here. Should we expand that? Yeah. So for lambda squared minus 2 times 2 times 7, that would be 28 lambda plus 49 plus lambda squared there. Well, the minus 0.16 here and here cancel as 10, right? If you divide both sides by 0.16, you get 10 on the left. So 10 equals 5 lambda squared, simplifying in the brackets, minus 28 lambda plus 49. Well, if I also subtract 10 on both sides, I have 39 here, yeah? Equals 0, right? Just checking, yeah? So if we solve, well, let me factorize it first, yeah? Let me try that. So I see 13 and 3 here because this is 39. It's not a prime number. So, yep, 13 and 3 can work. We have minus and minus, yeah? 13 plus 15 is 28. Okay, so lambda is 13 over 5 or 3. 2 possible values. We're done. Okay, number 3 is done. Okay, let's go ahead and do number 4. Okay, number 4 is a long one. A rough straight ram is fixed to the horizontal ground. The ram is inclined at an angle theta to the horizontal, where sine theta is 1 over 14. The points A and B are on the line of greatest slope. The ram with AB equals 18 and B above A. Okay. A package of mass 0.5 kilograms is projected up the ramp from A with the speed 8, as shown, yeah? Comes to instantaneous rest at B. Okay, loses all the kinetic energy at B. The work done against friction as the package moves from A to B is W joules. The package is modeled as a particle and air resistance is ignored. Okay, and the ram is also smooth in it. Rough is rough, actually, sorry. Okay, using work energy principle to show W equals 9.7. Good, okay. At least we know what to aim for. Well, yeah, work and energy principle. So It's moving up with some kinetic energy, so the lost energy will be kinetic energy. So you are losing kinetic energy from A to B, and you're gaining GPE as you go up. Yeah. Sometimes it's the other way around. If it goes down, then it would be the other way around. And then you also work against the friction there. Okay. Yeah, we will just do W there because they use W. And well, let's draw a little diagram as well, right? Because you have from point A here to point B. Well, you have a height change there, right? But this height change, which we need to plug in the GPE gained, well, the height here, because we know this is theta, and this is distance D, yeah? So we know the distance AB already. It's given us as 18, right? This is 18 then. So that means the height here would be 18 sine theta, right? So 18 sine theta would be 18 times, we know theta, yeah, 18 times 1 over 14. Just going to simplify to 9 over 7 first, yeah. Okay, so the height change is 9 over 7. So kinetic energy loss is 1 over 2. M is 0.5 V squared, because it's going to be from A to 0, so totally lost, like 8 squared here. You don't need to subtract anything because there's no speed at B. Yeah, instantaneous rest at B. So equals mgh, which is found to be 9 over 7 just now. Okay, and then the work done to overcome friction, which is just W. So we don't need to do anything yet, just W here, is it? Work done against friction as the package move, yeah. We're just going to prove that W equals that, so let's just simplify the math here. So this is 1 over 4. 1 over 4, that's 64, so that's 16. Yep, 16 here equals, that's just, what's that? Hang on, let me just get a calculator. 0.5 times 8.9 times 9 over 7, right? That's 6.3. Okay, is it? So if we minus that by 16, hang on. 9 over 7 minus 16. Yep. So if we subtract both sides by 6.5, we're going to get that. Indeed. Okay. As required. Part B. The coefficient of friction between the package and the ramp is mu. Find the value of mu. Well, not too hard there. Because work done to overcome friction here is going to be equal to F times 18, right? It's just going up. Work done is force times distance along the force. So 9.7 is equal to, friction will be F equals mu times N, which is mu times the, when you are moving up slope, the normal reaction is just mg cos theta, right? Yeah. So it's just mg cos theta there. So we want to find the value of mu. So mu times m times g times cos theta. Well, okay, we need to find cos theta, but that's not hard because they've given us the sine. So if sine is 1 over 14, so we put it like this, 1 and 14. We just find this adjacent, which is square root of 14 squared minus 1. 14 squared is 196. Yep, 196 minus 1 is 195. Root 195. Okay. So it's just cos theta. So root 195 over 14. Yeah. And then times 18. Don't forget. So this is mu mg cos theta times 18. And then we solve for mu, right? So mu is just, using a calculator would be wiser here. It is usually wiser because sometimes I'm dumb. I don't use it. Okay, that, not 9.8, square root that, divided by 14 down there as well, and times 18 down there. Okay, let me just double check the calculator. 0.9, 9.8 root. Yep, I think I'm okay with everything. So can it be a, yeah, I wouldn't go with that. So just do decimal here. Yeah, that would be it. 110. Okay, I think that makes sense. That's not too large or too small for a coefficient of friction. Okay, I'm gonna go with that. Now let's do number 5. We're at 24 now. Okay, coefficient of restitution, consecutive impacts now, I think, because you got 3 particles here. 3 small balls A, B, C have masses 2m, 3m, 4m respectively. The balls are initially at rest in a straight line on a horizontal surface with B between A and C. Ball A is projected towards B with a speed 5u, and okay, you know what, I'm just gonna copy, or maybe I'm gonna draw on the diagram here. Okay, yeah, and this is A being 5u towards B, and then A and B collide directly. Immediately after the collision, speed of B is 3u. Okay, so I'm just going to draw down here. After the first impact is just 3u here. Okay, the balls are modeled as uniform spheres with equal radii. A, find in terms of u the speed of A immediately after collision with B. Okay, just consecutive here. So conservation of linear momentum. Initial speed of A, so 2m, which is the A there, times the initial speed of A, which is 5u, plus 0 from the B will be equal to the total momentum after impact, which is, for the A, we are finding the final speed of A, so I'm just going to do VA there, yeah, after the first impact, plus 3m, which is the B here, times is telling us that the speed is 3u. So it should be going to the right, yeah, makes sense. Shouldn't be going to the left. So everything is assumed to be to the right here. We are just finding the VA there, yeah. So this is 10u equals 2VA plus 9u. Okay, so VA is just 9u subtracting 10u, we get u, and u divided by 2 would be A, VA, yeah, like that. That would be it. So everything is going to the right here, yeah. Okay, so let me draw that down here. This is to the right, speed of A immediately after the collision, so u over 2. And then B, coefficient of restitution. All right, so E is just relative speed of separation on the top divided by relative speed of approach. So the separation means that, well, because this has to be greater than that, so this is after collision, so we do 3u minus that. It's relative speed, so we need to do subtraction there. So 3u minus u over 2 divided by, and the approach is just 5u because B doesn't move at first, so it's just 5u there, guys. And of course u cancel, so we get 3 minus 1 over 2, so 3 minus 1 over 2 is 2 over 5, right? 2 over 5 divided by 5, that's 1 over 2 exactly, and u cancel. So that's it. Nice. Part C. After the collisions between A and B, ball C is projected towards B now with the speed u. Okay. So in consecutive collision, I'm just going to do this, yeah. That's where B has 3u and C is projected as u. B and C collide directly, yeah, saying here. The coefficient of restitution between B and C is F, given that there is a second direct collision between A and B. So that's implying that B will be reversed to the left again to meet A, yeah. Find a complete range of possible values of F. All right. So we do collision between B and C first, linear conservation of linear momentum, B and C, yeah. Conservation of linear momentum, B and C. So looking at the diagram here, so I have, let's do positive rightward again, yeah. So from B we have 3m times 3u now. That's when B and C will meet. Minus, right, because now C is moving to the left, so 4m times u from the C, yeah. Equals, well, we don't know anything yet, but we know that the speed of B will be to the left, right? And of course speed of C, do we know speed of C? Oh, we have the coefficient of restitution is F. Well, we're just gonna assume that, yeah, after the collision they going VB and VC here. I mean, we shouldn't confuse with the direction. If we convent rightward as positive, and if we don't know anything about VB and VC yet, I mean, we do know that VB will go to the left, but I would just make VB and VC to the right because we will find the coefficient of restitution and the coefficient of okay, let me just complete the conservation equation first. So that's just 3m times VB plus, right, because they both go to the right. That's what we assumed. Okay, like that. And we're going to keep this equation. Cancel m first. So 9u minus 4u here is 5u. So 5u equals 3vb plus 4vc. That's going to keep that as equation 1. And coefficient of restitution, so f, yeah, will be equal to relative speed of separation. So the vc and vb here will have to make sense now. So we do vc minus vb. So again, VB should be to the left, but when we say to the right here, VB will be negative. So when we do VC minus VB, it will self-correct. Yeah, I'm just saying that we can put this as VC minus VB. It should be fine. Relative speed of separation divided by the relative speed of approach. So that's just 3u plus u, right? Because they moving towards each other. So that should be more. So it's 3u plus u there rather than minus. Okay? Which is 4u. Okay, so this is f, right? So we are getting that, what are we finding? Find complete range possible of f. Okay, so we should find some f here. We should introduce some f in the simultaneous equation. So let's just put VC in terms of everything else, because we know that VB has to be negative already. So I'm just going to put VC as VB plus 4u f like that. Just multiplying 4u and move VB to the left with 4uf. So I get this equation here. Yeah, I think you're okay with that. So we're going to substitute 5u equals VB just kept the same, but then VC I'm going to change to VB plus 4uf like that. Yeah, and then have a look at this, simplifying this, plus 4VB plus 16UF like that, yeah. And let's make VB the subject, yeah. So we have a 7VB equals 5U minus 16UF like that. Okay, and then VB would be equal to 5U minus 16UF divided by 7. Yeah, let me check everything again. Yep, I think that's fine. And now we know that VB has to be less than 0 because it's going to the left, but we convented it to the right first, so we know it should be less than 0. That means 5u minus 16uf over 7 has to be less than 0. Now we can cancel the u, of course, because u has to be a positive number, so that's fine. We can cancel that. And we can multiply 7 here, doesn't change the sign there, so 5 minus 16f less than 0 still. That means f is, 16f is greater than 5, right, if you move to the other side. Yeah, so f is greater than 5 over 16. But f is a coefficient of restitution, so it cannot be greater than 1. That means f should be put like that. Yeah, complete range of possible values of f, and that's it. Yeah, so that's it, number 5. I'm just gonna skip to number 6 now, as in go to number 6. Wait, what? Why does it look so similar to the one we did before? Okay, a plane again. Smooth plane with incline angle theta to the horizontal with sine theta is 1 over 3, probably different. The points A, B, C lie on a line of greatest slope of the plane with B between A and C, A above B, AC 3A. So just everything shown in the figure. A light elastic string, okay, of natural length 2A has one end attached to the fixed point A, and the other end of the string attached to the particle P of mass M. Right. So let's draw out the diagram first. So A here, B here, C here. The natural length is 2L, right? And we just know that AC is 3A. Okay. The modulus of elasticity is that particle rests in equilibrium at point B. Okay. Equilibrium at point B. Okay. So this must be longer than 2A. Okay. Right. Show that AB is that. Yeah, we are finding it. So, okay. So, equilibrium means that it's stationary. So, forces balance here. We have force, which is mg sine theta here. And then we have the tension from the string. Yeah, tension from the string must balance mg sine theta. And then we, of course, have the normal reaction R and the mg cos here. That's nothing else. Just these forces, basically. So for part A, right, we can do T equals mg sine theta alone. Yeah? Is that right? Yeah, it should be. Okay, but T itself is the spring force or the string force, the elastic force, which is lambda. Let me just do on the other page. So lambda over L times X, which is the extension, equals mg sine theta is given to be 1 over 3. Okay? So if we find X here, we can add that to 2A and we get AB, because this is extension additionally to the natural length, right? Lambda was given to be, lambda would be the 8 over 3 mg, and L is the natural length, right? So 8 over 3 mg here times X divided by the natural length being 2A equals mg times 1/3. Just solving that, guys. The 3 here and the 3 here should also cancel. So we have X. That's not right. It's not giving me 9 over 4A somehow. Oh, because I haven't added it. Yeah, I just said that. So X is 1 over 4A, right? And then we have to add it in. AB equals 1 over 4A plus 3A. Wait, no. Plus 2A, right? Because that's the natural length. Yeah. So AB would be the extended length, which is the extension plus the natural length. And this would be, of course, 9 over 4A. Indeed. Yeah. Okay, so that's as required. Part B. The particle is now held at C and released from rest. So a little more extension down to C, some more elastic potential energy, yeah? And then it will be released. Find the elastic potential energy lost by the string when P moves from C to B. Elastic potential energy lost by string when P moves from C to B. Okay. Right, so it's just when it's at C, it's got some extension. When it's at B, it loses some extension, right? So we need to find the extension at C and at B and find the difference in energy, right? So delta elastic potential energy will just be, because we got extension at first. Let me think about that, hang on. Yeah, it will just be 1/2 K. I mean, for those of you who do physics, right? Probably most of you here watching should do physics. So the K value, the spring constant, is basically just lambda over L. So 1/2 K, which is lambda over L. Yeah, just make it more relevant to the paper here. And X squared, but if we find the difference, lambda and L are the same because lambda is the string property and L is the natural length. So when you find the difference between two energies here of the string, it's just X at C squared minus X at B squared then, and X is the extension, right? So it's just basically 1/2 times lambda is again 8 over 3 mg over L is 2A, yeah? Just put brackets there. And this will just be XL, XC. So XC, the extension at C, be careful, must be 1A because it's 3A minus, hang on. Yeah, 3A minus 2A. That would be the extension at C. And the extension at B, we already found it. It was 1 over 4, this guy, right? Yeah. So 1 over 4a, we just have to square that and do the subtraction there. And that would be the change in elastic potential energy from C to B. Yeah. Just consider from the string alone. Don't do anything else. Yeah. It's going to be in terms of MGA. Is that right? Yeah, that should be about right. Okay, the units is okay. So this is 2 mg over 3 for the outside the brackets. Inside the brackets, we have 4a squared minus 1 over 16a squared. Okay, so that's 4 times 16 is 64, so that's 63. 63 here. Yeah, over 16. This is mg. Where's the other a? Oh, it's here. Should be down here. Should be cancelled. A. So 1a here cancel with one of the a squared in there. Yeah. So I just got a here, and this can also cancel. So I got, this is 21. So to cancel that, 8. That's it. 21 over 8 mga. That should make sense because mg is a force, a is a displacement. So force times displacement is an energy. I'm just checking the units there. For those of you who are physicists, should know what I'm talking about. If you check the units and they multiply to the same units as energy, so this should work. At least, dimensionally speaking. Yeah. Let me check the math again there. Okay, so that is 21. 21 over 8 mg. That's 60. Yeah, yeah. I'm okay with everything, I think. Yeah, I'm just going to call it that. Okay, part C. Use the principle of conservation of mechanical energy to find the speed of P at the instant it passes B. Okay, so from C to B, you are losing elastic potential energy. So EPE lost will be KE gain, right? Yeah, because you are holding it at C, you release, and then you gain speed at B while also gaining some height, right? Don't forget. So you gain both energy here. Is it smooth, the plane? It should be, because we haven't seen anything about the coefficient of friction at all. Is it smooth? Oh, I haven't seen it smooth here. Should we assume that? Yeah, I mean, we're gonna have to assume that, right? Oh, smooth plane. Sorry, I was blind. Okay. All right. So there we go. We got it. So EPE loss, we got it to be. We're just gonna follow through that. 21 over 8 mga equals KE gain, right? So we find the speed. So it's just because at C it was held at rest, so no speed at C. It's just gonna be half mv squared, and we are finding this v here. Okay. Plus, now the height gained from C to B. So from C to B, right, along the slope there, well, it's basically 3a minus ab, yeah? Which is 3a minus, what was ab again? We got ab to be 9 over 4a. Well, it's in the question there. So this CB along the slope is just 12 minus 9 is 3 over 4a, yeah? Is that right? Yep, I think I'm okay with that. Okay, and that's just CB. But now we have to do CB. So CB is the hypotenuse, so CB sine theta will be the vertical side there from C to B, vertically up. So this is m times g times the height, which is CB, times sine theta, which is given to be a third, yeah? This one right here, yeah? mg, and then the height, which is CB sine theta. Yep. And then Yeah, I think I'm okay with that. I'm double checking here. Okay, yep, everything is fine. So m is cancelled here in every term. So we're gonna find v in terms of everything else, including the g and the a, because we are not told about the a value. So yeah, it's gonna be in terms of g and a. Maybe I'm just gonna make in terms of g and a. Let's see if we can simplify 9.8. Probably not. Okay, anyway, so v squared equals 21 over 8 GA minus what's that? 1 over 4 GA, and then all multiplied by 2, right? Because you need to move 2 to the other side as well. So what is that? Well, I'm just going to make this maybe 2 over 8, right? From 1 over 4. And then you're going to have what? 19 over 4 GA, like that? 19 over 4, because 8 cancel with the 2, I get 4. This is v squared, so v equals, well, it has to be a positive, so it's your square root 19 over 4 GA, like this. See if we can simplify that. I don't think so. Nope, so I'm just going to keep it like that, maybe. Well, let me try anyway. So I was wondering if we could do like 19 times 9.8 divided by 4. That doesn't simplify much. Yeah, ooh, we can do that, right? Well, let me put 7 over 10 root 95 times a, root a here as well. Although that doesn't get a lot simplified, but yeah, I'm just going to do an asterisk here to tell them that I got 2 answers, depending on which one they want to look at. All right, because it doesn't say in terms of g or a. Surely it has to be some a there, but we can keep g or substitute g as 9.8. I think, yeah, I think it's fine. I prefer the first one. You know what? Let me keep the first one. Yeah, okay. Next question, number 7, oblique collision now, which is more fun than the normal. Okay, so we got to be careful here. All right. 2 uniform spheres P and Q have equal radii. Good. The mass of P is 0.3 kilograms and the mass of Q is 0.4 kilograms. The spheres are moving on a smooth horizontal plane when they collide obliquely. Okay. Immediately before the collision, P is moving with the speed 5, yeah, as we can see in the diagram, 30 degrees. Q moving speed 3, 60 degrees. Everything is shown in the diagram. After the collision, they have V here and W here, good, as in plane view shown in figure 4. So this is basically from the top view, yeah. A show that V is that. Okay, so in oblique collisions, conservation of linear momentum is only conserved along the line of centers. They call that line of centers, yeah. So we just take the line of centers and conserve the momentum. So part A here, along the line of center, you have initial. So before collision, we have, if you resolve this vector to the right, yeah. I'm just going to draw it again, maybe. Okay. So you have before collision. Just going to do like, how should I do it? Maybe like this, yeah, before collision. And like this, right? Okay. Yeah, and then this and this before collision as well. Okay. So before collision, this will be 5 sine 30. And this will be 5 cos 30, yeah? For P and for Q, this will be 3 sine 60. This will be 3 cos 60, right? Okay, so this is 5 over 2. This is 5 root 3 over 2. This is 3 over 2. This is 3 root 3 over 2. I just happen to know all the basic trig values there, right? You can check in the calculator. Now, yeah, conservation of linear momentum along the center, along line of center, which is the one parallel to the line of centers there. Yeah. We have MP, which is 0.3 times the initial speed to the right. Let's convert rightward as positive. 0.3 times 5 cos 30, which is 5 root 3 over 2. Minus, right, because the Q is negative there, moving to the left. So mass of Q is 0.4 times 3 cos 60, which is 3 over 2. That's the sum of initial momentum equals, and then we want to find the speed of, okay, so after the collision, yeah, we're just going to do, yeah, so after the collision, it will just go like that, V. So I'm just going to use red pen here to denote after the collision, right? So V, this is V cos 60. This is V sine 60, right? And this will be W cos theta, and this will be W sine theta. Okay? All right. Okay. So, well, actually, you know what? Yeah, we could have just equate this to this, right? Because the vertical component doesn't change. The other component that is not along the line of centers doesn't change. We don't need to do this. All right. So we're just gonna do 5 sine 30. This is for particle P equals a V sine 60, and that's it. That should give us the V. Yeah. Okay. Didn't see that. Okay, so yeah, that's basically it. So V equals, if you divide both sides by root 3, it's just like, yeah, and then, okay, you get this first, right? And then it's going to be, if you rationalize the denominator, you get 5 root 3 over 3, yeah? That's part A done. Okay. And then this is next part, I think. So B, find the value of W and theta, right? Yeah, conservation of linear momentum along the line of centers. Yeah, so we get part B here. I did have the work there already. So after the collision, we have particle P again, 0.3. Now assuming that V is to the left, right? So we're gonna have a minus here. 0.3 times V cos 60 is just 1 over 2. And Q will be moving to the right, so I put positive here. Q has a mass of 0.4, right? Just checking here. Yeah, 0.4 times the speed of Q to the right, which is W cos theta. Okay, just put everything in there. Okay, just simplify this. We're going to have, we already know V, so I can plug it in here. But W cos theta is not known. Okay. Yeah. Again, we have another equation that, you know, W sine theta is going to be the same as 3 sine 60, right? So let me just put that as well before we do linear momentum here. So the vertical component of the Q should be the same. So 3 sine 60 is the same as W sine theta. Okay, well, it doesn't help much, but at least we can solve simultaneous, right? So this is basically saying W sine theta. Well, let me just keep it as the right hand side, yeah. So 3 root 3 over 2 equals W sine theta. Let's make this equation 1. And of course, if we simplify all this, we're going to get on the right side 0.4 W cos theta, and then you can divide the two equations, solve simultaneous, right? That's the trick there. So let me just do like this, yeah? So I'm just going to plug everything in the calculator. So doing fraction already, because I'm going to be dividing 0.4 at the end. So 0.3 times 5 root 3 divided by 2. Yeah? Just checking as I go along. 0.4 times 3 over 2. Wait, that's not. Or 1 over 5, let's say. And then that's the left-hand side. Yeah. Now, I move that term to the left side, I need to do a plus, right? Plus 0.3 over 2 times the v, which was 5 root 3 over 3. So 5 over root 3, you know, same thing. Okay, so that's moving everything to the left side already. And now we divide by 0.4 here. Oh, that doesn't look so simple. But okay, 5 over 2 root 3 minus 3 over 2 equals w cos theta. Okay, so that will be my go-to equation there. I mean, and then you can solve. You do 1 divided by 2, yeah? On the right side, you would have a tan theta. I mean, I prefer to solve for the angle first, and it doesn't matter here. They get both values at the same time anyway. And then let's put this as an answer and clear. So I'm just going to do, you know, 3 root 3 over 2 divided by all that, right? And yeah, so we just do 3 root 3 over 2 divided by answer, right? That will be tan theta. Yeah. So tan theta is that. Okay, let's hope that w is, yeah, I mean, I don't think it can simplify that much, right? It's let's make it decimal numbers, yeah. So yeah, it's fine. So theta is then arctan that, right? So arctan, that's already in degree. Okay, so theta is 42 point, I'm just going to put 552 here, degrees. Yeah, that means theta is that, and the w, does it make sense? Yeah, it should, yeah, should be less than, yeah, okay, yeah, I'm convinced. And then w, well, let's just use one of the equation there. So w is just 3 root 3 over 2 divided by sine 42.552 degrees, like that. Yeah, just plug in one of the equations. So I do equal here and clear again. So 3 root 3 over 2 divided by sine answer. So w is 3.84. Okay, so I'm just going to keep that as that, and the theta is just 42.6 maybe. Okay, so that would be my answer there for w and theta for part B. Yeah, I think I don't know, maybe there is some chance that I might have made an arithmetic mistake here, but that should be the right method, guys. Just gonna go ahead and do C now. I will know when I mark the paper later on. So find the coefficient of restitution between P and Q. So the coefficient of restitution in this case should also work just along the line of centers. Yeah. So along the line of centers, the speed of the relative speed of separation would be that minus that, or actually that plus that, because they go opposite direction. So v cos 60 plus w cos theta. Yeah, v cos 60 plus w cos theta divided by, that's the separation, the approach, right, would be this plus this, because they go head on in the same opposite direction there. So 5 cos 30 plus, what's that again? 3 cos 60. Let me just check the question as well. 5 cos 30, 3 cos 60, yeah. Okay, so that's the relative speed of approach. Okay, so we plug everything in. So I'm just going to write all the numbers, maybe a little tedious here, but we just have to do it maybe. V was proven to be, yeah, I'm just going to take that V. Cos 60 is 1 over 2 plus W, we just found to be, let's use a little more precise number, like that. Cos theta, so cos 42.6 divided by, wait, hang on, no, not like that, divided like this by 5 root 3 over 2 plus 3 over 2, like that. Yeah, checking all the math here. Okay. Yep, I think I'm okay with everything. Just plug in the calculator now. 5 root 3 over 3, right? Yeah. Times a half plus 3.842 times cos of, this is in degrees, so 42.6. Okay, and then divided by, well, let me just, you know, it's a follow through, so I need to just do that maybe. Okay, not too precise there. Okay, right, so that is just 0.732. Yep, I'm gonna go with that because it looks fine to me. Yeah, coefficient of restitution between P and Q. Just take the ones on the line of centers, yeah, not any other components. And that's it for oblique collision. All right, it took a while. Okay, we still have another one. This is yeah, okay, also collisions, but you know, oblique with the wall, not with not between particles. Figure 5 represents a plan view of a part of a smooth horizontal floor where RS and ST are smooth fixed vertical walls. Okay, the vector RS is in the direction of I, ST is in the direction of that, right? Okay, a small ball B of mass 0.25 K is projected across the floor towards RS. Okay, at the start here, immediately before impact with RS, the velocity of B is V. Okay, immediately after the impact with RS, the velocity is that. Okay, coefficient of restitution between B and RS is 1/3. The ball is modeled as a particle. Show that kinetic energy lost by B in the impact with RS is 4 joules. Okay, it's just the first impact here. We're going to focus on that first. Now, with the wall, right, works the same way, exactly the same way. You just consider, okay, let's say there is a ball here. And when the ball, the small ball, B, arrive, yeah, this is the path there, arrive at the wall, we consider the line of centers kind of thing here. So we consider just the perpendicular direction at the wall. That's when it hits the wall, right? Actually, the particle should be smaller, but I just enlarge it a bit. Okay, so the other direction, the speed doesn't change for the particle. Okay, so let's make it alpha, and so this will be beta, right? At RS first. Okay, so basically we have a V here, incoming speed, and then we already know the speed of velocity of B after the impacts, right? So we can find the angle beta as well using just the vector here, yeah? So this is indicating it's going to the right by 3 unit, rising by 2 unit. That's the like the slope there. You can find the angle here. This is just vector. And also telling you that the speed towards the right is 3, upwards is 2. So that means the horizontal component of V here should also be 3, right? So we can calculate a lot of things here. Kinetic energy lost by B at impact is 4. Okay, so we're just going to have to find V basically. Okay, so I'm just going to write something first. Consider along the, you know, RS here, where momentum doesn't change, right? So V cos alpha is going to be equal to 3, because the horizontal component, you don't need to find beta here, you just take 3 here because it's already telling you that 3 to the right and 2 upwards, right? And that's one equation. Now we also given the coefficient of restitution. That means, I mean, if you do, if you resolve V here, so basically going in, V, the vertical component of V would be V sine alpha, right? Yeah. And then you have beta, sorry, the final velocity here going upwards. If you look at just the vertical component, it's just 2. So going upwards by 2. And that will allow us to calculate the coefficient of restitution. At least the coefficient of restitution is 1/3 is given. So we put that equal to, again, the formula, speed of separation. Relative speed of separation would be 2 minus V sine alpha there. Wait, it should be plus because they go in opposite direction, as we can see. Yeah, should be put relative. So if they go opposite direction, you add them up. Divided by, yeah, wait, hang on. No, that should just, no, okay. This is with the wall, so it's just, sorry, it's just, so the separation 2 should be less, so this is 2 divided by V sine alpha. The wall doesn't move, sorry. Yeah, it should be the final speed. If you hit the wall, right, if the ball hits the wall, it's just the final speed over the initial speed equals the restitution coefficient. Yeah, or the coefficient of restitution times the initial speed equals the final speed if you hit the wall. So that's just it. Yeah. Okay, so we have 2 equations now. I'm just going to make V sine alpha the subject. So you have 6 here, right? So that means tan alpha again. Wait, hang on. Yeah, tan alpha is 6/3 is 2. Because I have to do V sine equals 6 divided by V cos equals 3. Yeah. Okay, so we get the alpha value now. What do we want actually? Yeah, we want to find V, right? Okay, so can we make it exact? Yeah, we could. So if tan alpha is 2, I'm just going to use this trick again. It's 2/1, so this will be √5, right? That means cos alpha is 1/√5. Just using this trick, because tan alpha is 2, you can just put 2/1 there in the so-called TOA triangle. And then you find the hypotenuse, you get the cos, the car, 1/√5 there. And that would allow me to calculate the V, right? So V equals 3/1/√5, which is 3√5. I want exact value there, basically. Yeah. Okay. So we want kinetic energy, right? Lost. So KE loss is just 1/2 times the mass, which is 0.25 times, well, it should be greater before hitting the wall. So before hitting the wall, V is 3√5, so that's 3√5 squared minus, after, well, you can do both components squares and add them up, right? Or you can find I mean, it's the same thing here. You can do Pythagoras and square it. It's going to give you the same thing. So it's basically 3 to the 2 plus 2 to the 2 here. Okay? So that's 1/4 outside the bracket. No, it's 1/8. I almost made a mistake there because 0.25 is a quarter. And this will be what? 9 times 5 is 45. Minus, so that's 9 plus 4 is 13. So what is that? 32, good. 32 divided by 8 is 4. Yeah. That's kinetic energy lost. Oh, 4 joules. We proved it. Okay, good. Part B. Immediately after the impact with ST, the velocity of B is W, meters per second. Immediately after the impact with ST, okay, so another one again. Given that the coefficient of restitution between B and ST is 1/3. All right, so another one here. And now ST is along the direction of, hi guys, just a quick one here. This statistics always blows my mind. So as you can see, for the past 28 days as of today, 90% of those watch hours come from those of you who aren't subscribed to my channel. And that gives me an urge to beg you, please help support me by subscribing the channel. I will return this huge favor by creating more and more videos. I'm going to utilize my teaching experience for 10 plus years to create the videos covering tips and tricks and the hard bits in the topics that most students struggle to understand. It can either be a short video, a long video, but they will sure come up. So that is why you need to subscribe to stay tuned. I hope we have a deal. Let's get back to the walkthrough. So it's given that this vector is along the direction of 3i plus 4j, right? That means we know this angle. Gotta be careful with that. So this angle is just alpha, where tan alpha. You can just find tan alpha by doing 4 over 3 there, just solving the vector there. It's like finding the argument of the vector. Okay, just writing that first. And yeah, the ball hits like this. Okay, and then it's gonna bounce like that. So it's gonna lose some speed, and you know, this angle will be smaller than this angle usually. Okay, and we want to find the velocity of B, which is the W there. Okay, coefficient of restitution is 1/3 again. All right, so what should I do with this? All right, okay, I mean, we shouldn't do X and Y, right? We should do along perpendicular and along the wall anyway. Okay, let me think about this a little bit, because it's a little tricky, but yeah, we should find this angle first, I think, for sure. Okay, let's solve some geometry there. So if you sort of draw out the triangle, we already know this angle right here, right? It was, yeah, we can find that. So let's make this theta. Theta equals, well, again, it's this vector here, so you can do arctan 2 over 3, right? Okay, that angle there. And, well, this angle will be that angle minus that angle, right? If you do the triangle here, I mean, you know this angle alpha, just doing arctan 4 over 3, and it will be, so this angle will be 180 minus alpha, right? That means this angle, if you do 180 minus this and this, you get that. Okay, so let's put this as not, so this will be arctan 4 over 3. I'm just going to do that already, yeah. And this will be then alpha. Okay, so I'm just going to do alpha equals arctan 4 over 3 minus the theta there, which is arctan 2 over 3. Yeah, let's solve that angle first. Arctan 4 over 3 minus arctan 2 over 3, right? Yeah. Okay, so I get, gonna go quite precise here for 0, 0, okay? For that alpha angle, which is the angle between the second impact and the inclined wall there. Weird, okay? But anyway. And yeah, we can solve this to this direction and this direction now, right? So let's just draw this again. So we have the velocity. So let's say this is the point of impact. The velocity along the wall would be, so what's the, okay, this is the V, right? It's the V. I'll make it U, yeah? So that would be 3i plus 2j. And it's just going to be U. We just find the speed, yeah? So the speed is just root 9 plus 4, which is root 13. You just find the Pythagoras between 3 squared plus u squared, yeah? And then I'm going to make that as a speed because now we change the angle. It's not in the normal axis now. So this will be u, or root 13, I say, times, if you want to resolve to this, right, you do cos alpha. So cos alpha here. And the perpendicular direction to the inclined plane would be root 13 sine alpha instead, right? Just the way you would solve in the normal axis, it's just inclined, yeah? Now, again, we know that the 13 cos alpha should be the same, right? So this, after the impact, would be 13, root 13 cos alpha, again. And this will be changed now. because we know that the coefficient of restitution is 1/3, so that should be 1/3 times root 13 sine alpha. Simple. Because and then multiply, yeah, okay, I already multiplied that 1/3. Right, now we want to find the W, right? So basically, this will be equal to root 13 times, yeah, it's not going to be a nice number here, right? We can't make it too nice. Cos of, yeah, let's make that already. So put that in the calculator, I mean. So we already have the angle there, so I'm just going to equal that just in case. So it's root 13 times cos of answer. Ooh, I'm lucky. So it's just 7/5 there. All right, it's good that I didn't round the value here. Okay, so I should do that with the sine alpha as well, right? So I should clear this first, right? So somehow we can simplify that. Okay, so times 1/3 times sine of answer. Yes. So this is 2/3. Okay, so that should make sense at least. Wait, hang on. Yeah, okay. As you can see, now we get the two components, but this is not along the I and J direction. So we want to resolve this in the I, and this in the I, and this in the J, this in the J, yeah? Okay, so we're just going to resolve those two vectors. This is going 17/5 that direction. This is going 2/5 in that direction, and we know the angle here, right? So this is still alpha, right? This is still alpha, isn't it? Yeah. And what's the other one? This is 90 degrees, so that should be 90 minus alpha there, right? Okay, so we're going to keep these two values as exact values and then find W in terms of I and J. So basically we just resolve the components along the I and along the J. Yeah, so you should get 2 in either directions. So W is just going to be to the right, yeah, positive to the right and up, right? Because that's I and J there. So we have 17/5 cos alpha to the right minus, because you also have 2/5 to the left, so you need to subtract sine. So you have cos 90. Sorry about that. So you have cos 90 minus alpha. That's basically sine alpha. Okay, that's for the I alone. Plus, I'm just going to write down here for the J. So it's just the opposite. So it's 7/5 sine alpha plus 2/5, because they both go upwards, cos alpha instead, and this is J. Now I was wondering if I do cos alpha and, alpha, right? We already know that alpha is, we already know the exact value of alpha, right? Wait, no, hang on. I mean, alpha it's not alpha, it's, let's put this as gamma, maybe. Yeah, so, wait, hang on. It's along this and this, right? Yeah, this is also gamma. Yeah, okay, they're gamma. We already know gamma. Because it's just, you know, we were given that tan gamma is 4/3. Because it's 4 and 3 there. This is the vector, 4/3, right? So gamma is this guy, and then we were given that is 3i and 4j. This is the direction of this plane here, the ST plane. Yeah, this is ST. So we know that angle. That means this is 5, right? This is a right angle triangle. So sine gamma is just 4/5, and cos gamma is just 3/5. So we're just going to plug everything in there. So 17/5 times 3/5 minus 2/5 times 4/5 I plus 17 over 5 times 4 over 5 plus 2 over 5 times 3 over 5 j. Yeah, so what's that? 20, that's not 21. 17 times 3 is 51. 51 minus 8, so that's 43 over 5i. Is that right? 51 minus 8, yeah, 43 plus the j, so that's 68. Yeah, 68 plus 6 is 74 over 25. I forgot, this should have been 25. Yeah, j. Yeah, okay, and that's it. That's w in terms of I and j. Yeah, as a vector, and that's done. And that is the end of the paper. I just realized that, so I had 2 minutes left. Not gonna double check anything, so I'm gonna mark the paper and see you in a bit. Yeah, okay guys, I've marked the paper and I lost 6 marks here. Let's go through them. So the first one is on question 5. Yeah, so it's on part C. Find the complete range of possible values of f, right? So I did say that that for B to hit A again, the direction of motion of B after hitting with C should be reversed. But that doesn't need to happen because I didn't think about this case where B is moving to the right and A catches up. That can also, allow the second collision between A and B. And let's just find that condition, right? So we already know that the VA after the collision with B at the first time is u over 2, which is directed to the right, okay? So for A to hit B again, this speed must be greater than VA, assuming that this is also to the right, because at first I set it to the left, so I put it to less than 0, but if you remember, we assumed that VB, when we did the linear conservation, the conservation of linear momentum and the coefficient of restitution, I said VB directed to the right. So that means we need to do VA, yeah, greater than VB. VB after the second collision with C, right? So VA was u over 2 greater than this guy, which is also to the right. Yeah, if we set that, we're going to get this. As you can see, we can cancel the u. Yeah, if we cancel the u, what's going to happen? Well, we have 1 over 2 greater than 5 over 7 minus 16 over 7f, right? And if you solve that inequality, let's just delete this thing first. You're going to have 1 over 2 minus 5 over 7, so that's 7 minus 10, so minus 3 over 14 greater than minus 16 over 7f. So if we swap the sides, we have 16 over 7f greater than 3 over 14, and we cancel this. This is 1, this is 2. So basically f has to just be greater than 3 over 32. Yeah, if you multiply that out. And as you can see, this is less than what I got before. Because what I got before, it's in the condition where VB has to be reversed to the left. But this F allows that VB can still go to the right, but just slower than VA. So VA catches up. The particle A catches up and hit B again. Because we don't need to talk about C. C won't be caught up anyway because C is going faster than VA after the collision with B and C anyway, right? So we don't worry about that. VC will be fastest anyway and A will catch B up, right? So the correct answer would just then be this instead. Yeah, for that. All right. Let's look at the next question that I should correct, right? Which is this one. Yeah, this one I made a silly mistake. I did say that it's about the energy loss. Yeah. So I lost mark in part B and then part C I follow through. So part B here, I did put this wrong. It's the extension at C. And I did say that because we already have 3a as the extended length, so the extension should be just 3a minus 2a, and that should have been a, not 2a. So this guy should have been a here. Yeah, this guy should have been a, and this should have been just a as well. So in the brackets there we should have 15. So this should have been 15 over 16, right? Yeah, if you correct that. And then that means this should have been 5 over 8, I think. Yeah, just cancel everything. So yeah, that should be right. 5 over 8 mGa instead. Yeah, and if you use the right value for this energy loss in here, yeah, so that should have been 5, right? We should get, if we solve everything, so this should have been 5. So that would be 3 instead, right? So that would be, yeah, so it should be root 3 GA over 2. Yeah, that should be the right answer there. Okay, so that's just for number 6. And the oblique collision here, everything is good. And this one, the oblique collision with a wall, did I make any mistake? I didn't, so everything was fine. So let's do a review on the whole paper again. Yeah, I think overall the paper is not too easy, not too hard. I wouldn't say easy now. Yeah, if you don't, study through the contents thoroughly here, it can be tricky, particularly the collisions, right? Make sure you learn all the conditions in those. Now let's go through each of the questions, yeah, individually. Question 1, I think is still fine. This is mostly AS stuff. I mean, you could have done it. The AS student could do this question. Yeah, it's kind of like AS stuff here. There's no vector, it's just impulse and momentum. Yeah, so it's still fine for this one. And number 2, yeah, still okay. So I think the first few questions are quite okay, right? It's not necessarily A2 stuff. Yeah, this one, energy, force equals P over V, yeah, for the force from the power there, yeah, and it's just Newton's second law. This could even be pure math actually, apart from the P equals FV equation. This is also okay, right? This is not too bad. Number 2. Number 3, yeah, things start to get a little more advanced. Now, this one isn't too tricky. It's just that you need to know that we can find impulse from change in momentum, and because they ask you to find the lambda here, that's why they give you the magnitude. This is just plugging in the values in the equation straight, not too tricky. This one, yeah, this is where I lost. No, I didn't lose any mark here. Okay, so this is still energy, and now you have work energy principle, right? Yeah, so this is like a warm-up for later on, where you have more advanced energy conservation, like the string one, right? So for this one, yeah, make sure you understand how to go from loss and gain, or usually the energy loss is on the left side, and then you have energy gain and plus some work done against friction. It's just you have to figure out whether to put KE for the loss or gain. Sometimes you are gaining KE, like if you are going down, yeah, you're losing GPE and gaining KE. That can be the case. And sometimes later on, as you can see, you also have EPE, playing some role in there as well. Yeah, in this case, just kinetic and gravitational. So it's still fine. Don't forget that the work done against friction, it's just force times distance along the force. Yeah. So this one is fine, I think. This one starts to get a little harder now, because you have consecutive collisions, successive impacts, yeah, between multiple particles here. Yeah, I made a fundamental error about the condition where A and B will collide again, so that might be tricky. But I mean, if you guys get it, that's good. That's good. Yeah, you're doing great. So here, I think the first two parts are fine. It's just that make sure you understand how it's, in this kind of collision content, you just have coefficient of restitution and conservation of linear momentum. Again, just make two equations and solve simultaneous. Make sure you take care of all the signs and directions very thoroughly, yeah. Gotta be careful for that. And yeah, for the last part here, I just missed one key fundamental there where A and B collide the second time, so A can catch up. So you probably need some physical interpretation there in your mind to make this correct, right? Not just remember. Don't go memorize anything here, but understand. Yeah, understand the physics context of that, right? Like what's possible and what's not. Yeah, usually the hard bit is about finding the range of values of these coefficients, right? So for coefficient of restitution, you need to know that it cannot exceed 1, got to be greater than 0. But then the lower bound is a tricky part. Yeah, the lower bound here, I got it wrong first, right? So I would stress that. And yeah, this is a little more advanced work and energy principle. Here you have EPE playing a role as well, but I think the question, do a step-by-step there so you wouldn't be lost after you have found the elastic potential energy loss here, which I got wrong because I put the wrong extension in there, a silly mistake. Although I did say about 2A and 3A there, but I put 2A in, okay? And yeah, so here you have, because you hold it at some point with some extension and then you release. So you are losing EPE, gaining KE and GPE together as you go up, right? Because when you go up, height increases and speed increases too. So you are gaining two types of energy there. And then if you solve that equation, you would get the right answer here, okay? Oblique collision, yeah, make sure you understand the two key fundamentals, I would say. Coefficient of restitution and conservation of linear momentum only applies to the line of centers. Yeah, I mean, in the direction of line of centers there, like the dotted line, you would have, if you resolve the momentum to the line of centers, total momentum before and after is equal. So just along the line of centers. And also the coefficient of restitution only work along this line of center. Okay? And the other key fundamental here is that along the perpendicular to the line of center, everything is the same. If you take the analogy to, so the analogy of this is just projectile. So in projectile motion, the horizontal direction, everything is the same. No acceleration, speed constant. Yeah, this is analogous to the vertical, like the perpendicular direction to the line of centers there. Yeah, just the same thing. So when you know that, you can, like for example, for part A, you can just find the required speed here by just doing, because before it was 5 sine 30, so after, which is v sine 60, so they are equal because the perpendicular direction to the line of centers, speed is constant, okay, for either particle, right? That's why A was not that hard. And then later on, of course, you need to, talk about again the conservation of linear momentum and also the coefficient of restitution. It's just basically this paper has about 4 collision or impulse questions. It's just that you have normal, like head-on collision and oblique collisions. But the fundamentals are really the same. It's just the difference is about the line of centers. That is the only key difference. So if you understand this perfectly, everything will just be easy. I mean, apart from making silly mistakes like I did once there. So yeah, just understand the fundamentals here rather than memorizing how to do, right? That's very key. Particularly if you want to go study engineering, I recommend you emphasize understanding rather than memorizing. It will take you, you will go further along the course and not struggle as much. Yeah. And yeah, just solve simultaneous. The rest is just math, right? I mean, if you understand how this works, the rest is just math. And this is just the coefficient of restitution. Again, it's just along the line of center. I take the relative speed of separation along the line of center from either particle. Yeah, so v cos 60 and w cos theta is the v cos 60 is here, w cos theta is here. They are both the components of velocity along the line of centers after the oblique collision. Yeah, and the one before is just this guy and this guy. The one after is just this guy and this guy. Make sure you take care of the signs, because relative speed, when they go in opposite direction, they add up like these. Yeah, okay, and that's fine. And yeah, this one I would say is relatively hard about the directions, everything, because they do consecutive oblique collisions with the wall there, and it's still the same principles as before still apply, because this is still oblique. It's just not between two particles, but between a particle and a smooth wall, right? So there's no friction here. That's good. So same thing applies here. It's just now you have a wall. This should be easier. The thing that might be harder, so this is fine, I guess. Yeah, you just find speed before and after. You find everything you need, so you would have difference in kinetic energy. Use the same principle there. The thing that is hard is probably part B. And I would like you to make sure you understand this question again. Maybe go back to the walkthrough again to see how I explain through this. It's just that this collision is harder. Yeah, so the first collision was fine. You got the speed here, but relatively hard because you got to figure out these two angles, right? If you can figure out those two angles, you are halfway there. The last step is just to put, the w here, the velocity vector after the second collision there, to the right value. And this is just geometry. So you figure out the angles between the lines and everything, and then it's just going to give you the value here. And I was lucky that I kept all the significant figures in the calculator, so I realized that it should have been the exact values there, right? You see, so if you don't, I mean, if I didn't do them as these, and let's say there was one step that I kept this angle in the calculator, and I use it again later on, so I realized that it should have been an exact value somehow, right? So when I put them back to this, they're all exact, and the answer should be exact, I think. Maybe the actual mark scheme, which as of the time of recording is not out yet, so maybe the mark scheme when it's out, they're gonna allow some decimal places, but because the question doesn't say, right, does it? The question doesn't say exact, so we never know. I mean, but the exact answers always, always work. Except maybe in statistics they prefer decimal place answer. I don't think they ever ask for exact values. Maybe not. So you should change to decimal places, but probably not mechanics and not pure math, right? So yeah, I was stressed about this. Is probably the best question in this paper in terms of the blend between hardness and the merit of the question here. That makes the paper legitimate and a little harder. Yeah, so part B here. If you don't understand, go back. And that was it, guys. So I hope that was all useful. Again, do check the playlist in further maths, in other papers. I've walked through more papers than you might know. And check out other videos too. And I hope to see you in the next one. Bye.